Hello, welcome to our optimization project. So let me just introduce it in this video. So I'm going to switch over to a screen share. Okay, and I believe I'm recording again. So as I go through this project, I just wanted to highlight one guideline that wasn't mentioned clearly in our last portfolio, and that is that I don't want you to seek out any answer keys, okay? No using, I guess, solution keys. Okay, I'm sure in this day and age, if you look hard enough, you can probably go out and find solutions to all of the problems in our textbook. I don't want you to do that. That would be considered plagiarism. So do not do that. If you already have one of those, just set it aside while you're working on your portfolio. I don't want you to use outside resources. Okay, you can collaborate with your classmates, and you can ask questions of me. But I want you to sort of wrestle through these problems. So you can collaborate with classmates. Okay, you can't copy their work, but you can ask them for suggestions. All right. So what we are going to begin is our optimization portfolio. So right here is a first example problem of the kinds of problems that we're going to be working with. Okay. So we're supposed to find two numbers whose sum is 80, which maximize their product. Okay, so what I want to do is I'm going to lay out a way that we're going to approach these problems. We're going to set up a little grid, okay? And the top part of the grid, we're going to end this grid here. The top part for every problem will be verbal, okay? And then the bottom part will be algebraic, all right? And the first column will be the thing we will optimize, and the second column will be constraints. Okay, so pretty much every problem will fit this pattern. So as you read a problem, you can fit it to this grid, and it will help you to figure out what to do. So the first thing you do as you're reading the problem is don't worry about the algebra. We're going to get to the algebra second. We're going to worry about the verbal thing first. If we can't state it, it's going to be hard to write an algebraic expression for it. Okay, so the first thing we have to do is read the problem. And so it says we're supposed to find two numbers whose sum is 80, which maximizes their product. Okay. What we want to do is we want to maximize. You could just write the word max a product. Okay. So that's what goes in the first column, right? The constraint is that the sum of two numbers is, what did I say, 80. Okay, so that's a constraint. Because if you could take any two numbers you wanted and find their product, the product could get infinitely large. But the constraint is that the sum of the two numbers can't be more than 80. All right, now let's make this algebraic. We need two numbers, so we'll give them variable names, x and y. All right, x times y will equal a product, p. Or we could write p equals xy, maybe that's better. But we know that x plus y, this is the constraint, is 80. Okay. Sometimes it might be less than or equal to 80, but we'll just assume that it's at its biggest possible sum as we're trying to optimize the product. Okay, so how do we do this problem? Okay, well, we need the product to be optimized. All right, so we're going to need a derivative of the product. But if we start with p equals xy, there's a problem. Okay, right now we have two inputs. In order to do all of these problems, you need to get down to one input variable. Okay, and that's where the constraint comes in. Okay, the constraint says that x and y can't just be any number. All right, if we know what x is, since x plus y, let me write this down here, is 80, we could substitute that y is 80 minus x. So now let's substitute the constraint back into the product, and we can say that the product is x times 80 minus x. All right. Now, this is what we're going to want to optimize, okay? And to optimize it, we want to find a maximum, okay? To find the maximum of this, we're going to want to take a derivative and find where it's 0 or does not exist. In this case, it will be equal to 0. So it's much easier to take the derivative of p if we rewrite this as p is equal to 80x minus x squared, okay? Now you can see, well, we could take dp dx, here's the calculus of it, and we would determine that that's 80 minus 2x, all right? We need to find the critical points of p. So to find the critical points, I'll move over here now, the critical points happen when dp dx equals 0. So 0 is equal to 80 minus 2x, okay? So 2x is equal to 80. So x is equal to 40, okay? Well, now we have to figure out if that is, in fact, going to be, give us a maximum, all right? So it's very important that we do a derivative test. So let's make a number line. Now, there is no limit on x being positive or negative. So let's put a number line right here where x equals 40. And let's test a number that would be relatively easy to use below 40, like x equals 20. And we will test a number above it, like x equals, let's say 60. And let's plug those into the derivative and find out what is true about dp dx, all right? When you put in a number like 20, you realize that you get 80. We're going to put that into dp dx here. And so that will give me a positive value, okay, for dp dx. If we put 60 in, we will get a negative value. So what did we just show? dp dx changes from positive to negative, so the function must have been going from increasing to decreasing. So this does verify that we have a maximum at x equals 40. Now, we haven't yet answered the problem completely. We're supposed to find two numbers. So if x equals 40, we can go back up. X equals 40. We know that y is equal to 80 minus x. So 80 minus 40, it is also 40. So the two numbers that we were looking for were the numbers 40 and 40. We would want those numbers to happen twice, all right? We could have done a second derivative test here. I'm kind of running out of room here. But if you wanted to, instead of doing a first derivative test, this would be a classic example where it'll be very easy to find the second derivative of p with respect to x. That's our notation for that. And if you look at that, when we take the derivative of dp dx, it would be down to just -2. And so this guarantees, since the second derivative is always negative, this also gives us a max at x equals 40. Okay, so this shows that we're concave, the graph is concave down everywhere. So we must have a local max by the second derivative test. When we're at x equals 40 or any value, the second derivative is -2. Therefore, at x equals 40, that must have been a local max. So in this particular problem, the second derivative test might have been more useful for proving that we had a maximum when x equals 40. So the answer is that the two numbers are 40 and 40. Let's move on to a second example that's closely related to that. We're supposed to find two positive numbers whose product is 32, which minimizes their sum. So this is really just turning the other problem on its head. Okay, so let me make a table that's a little bit smaller. We have verbal. And then we'll have our algebraic. We need to optimize. And we're going to have constraints. Okay, so here's my little box. Let me get rid of some of this extra. Make sure this is a pixel eraser. There we go. Okay, so Get rid of this. Okay, so that's a neater box now. So in this case, as we read the problem, we want to minimize the sum. Okay, so the thing we're going to optimize is always a maximum or minimum. So in this case, we will have I'll just write min sum. We want a minimum. You can write max or min just to shorten it up a little bit, but we want the minimum sum. Okay, but the constraint is that the product is 32. Okay, so we want to minimize the sum of two numbers. Maybe we should write of two numbers, okay, whose product is 32, right? So over here for constraints, I can write P is X times Y. We'll call the numbers X times Y. So X times Y is 32 would be my constraint, all right? Maybe, in fact, I might want to get rid of the P and just keep track of X times Y is 32. All right. The sum X plus Y is supposed to be minimized. Okay, so let's say, in fact, let me just paste this and write it the other way. I'm going to write S is equal to X plus Y. So we're going to minimize S, right? So let's do what we did before. Probably should be better off starting underneath of my box here. So the sum is X plus Y. Once again, we can see we have the problem of having two inputs. We need to get this down to 1. So this is where we use our constraint. We know that X times Y is 32. So let's substitute out Y. So we'll say that it's 32 divided by X. All right. So that means we can say that S is equal to X plus 32 over X. Okay. Now for taking the derivative, you might find it useful to call that X plus 32 X to the negative 1. Right. So let's come on up here and we'll right over here do what ds dx is. ds dx is going to be 1 minus 32 X to the negative 2. All right. So just using the power rule. Now, in order to find where this thing is 0 or undefined, we want to write it in a rational form. So you can see that this would be nice if we were to multiply everything here by x squared over x squared. Our job is going to get easier. We'll be closer to solving it. So ds dx, we'll have a denominator of x squared, and then we will end up with x squared minus 32 in the numerator. Okay. Now I believe, say find two positive numbers. Okay. So obviously, okay, we can't have, in looking at this, we have to evaluate the possible solutions. So we want to find, critical points of this. So we want to find where ds dx equals 0 and where it's undefined. So we're very interested in where 0 is equal to x squared minus 32, or 0 is equal to x squared. This would obviously be x equals 0, but then the product, y would have to be infinitely large in order for this to work. So this simply doesn't work. You can't have 0 as one of the solutions. It would make the derivative undefined, but that clearly isn't going to be a logical solution to this problem. So we're now over here, x squared must equal 32. Okay, so x is equal to plus or minus the square root of 2, but the problem stipulated that this thing was in fact a positive number. Okay, so it looks like the square root of 32 is the best that we can do. All right, or that is the answer. So we want x to be the square root of 32. Now we need to prove that this in fact gives us a minimum. All right. So given that this one is a little bit trickier, we'll stick with a first derivative test for this. And let's make our number line. Square root of 32, okay, is right here. Now let's put in, we want to evaluate ds dx. And let's pick a number that's clearly less than 32, but positive. Let's pick a number like 1. This should be x equals root 32. So if you put 1 into our derivative right there in its kind of most basic form, clearly it's negative when you put in 1. And then let's just put in a really large number up here. Bigger than that, we could put in a number like 100. And if you put in a number like positive 100, clearly dx will be positive. So those are great test points. So the first derivative clearly changed from negative to positive. Therefore, the function went from decreasing to increasing, and therefore, this is in fact, it verifies that we have a minimum. So we've just verified the min using a first derivative test. Now the last thing to do is we're supposed to find the two numbers. And so we know, going back to white here, that y is equal to 32 over x. So 32 over the square root of 32, which is also the square root of 32. So we have the solution that x is the square root of 32 and y is the square root of 32. Those would be, those are the solution to the problem. And we have verified that that would give you a minimum sum. Okay. Now what I want to do is one last problem, and it's textbook problem number 10. So you can pause this video and read the problem to yourself. Okay, so P is representing sort of the amount of photosynthesis that will take, and I is the intensity of the sunlight, right? So we want to figure out what intensity I will give us the most photosynthesis, right? So when I look at this, if I'm going to make my little table, that's a requirement for all the problems in our portfolio. We have a verbal, okay, we have algebraic, and you can see we already have an algebraic expression here. But we need to write down what is it that we're going to optimize. We need to make sure that we are doing the right thing as we do the problem. Okay, and then we have a constraint. I should have left a little more room in here. But as we look at this, we want to maximize the photosynthesis. I'll just write photo in here. I should have left myself more room. The constraint is the equation, the given equation. Okay, so we can just say what is it that we're going to maximize? We're going to optimize. So algebraically we have this constraint equation. P is equal to 100 I over I squared plus I plus 4. We're also going to be optimizing P, so it kind of goes in both boxes in this case. So we want to make P a maximum, but we're also constrained by the relationship that we have here. So this one, you basically just have to find dPdI. We're down to one variable already, so we don't have the problem that we had before of needing to use the constraint, okay, in order to eliminate a variable. So we just have to find the derivative of this, okay? Now this is a quotient rule problem. So the denominator, when we take the derivative, is the original denominator squared, all right? When we go to do our crisscross, we'll have 100 times I squared plus I plus 4. That's our U prime V minus UV prime, that's 100 I times the derivative of the second equation, the denominator, so 2I plus 1, all right? And then we better simplify this. So it looks like the numerator has 100 I squared. Well, let me just expand this. 100 I squared plus 100 I plus 400. minus, it looks like we're going to have 200 I squared minus 100 I all over I squared plus I plus 4. Well, that should be squared. All right, and then we have 100. So if we look at this, it looks like we have negative 100 I squared. Okay, and then we have the 100I and the negative 100I look like they cancel out. Just double check, that looks right. Okay, and then we have plus 400 in the numerator all over I squared plus I plus 4 squared, the quantity squared. All right, now we need to find out where this is 0 or undefined. Okay, now the denominator, since I has to be greater than or equal to 0, the denominator never goes to 0. So we only need to worry about, since that's true, I squared plus I plus 4 cannot equal 0. Okay, so we can eliminate needing to look at the denominator in this case. So we just have to look at the numerator. So find out where that's 0. Negative 100 I squared plus 400. Set that equal to 0. Bring the 100 I squared to the other side. Whoops. My eraser out. Divide by 100. So I squared is equal to 4. So I is equal to plus or minus 2, but we can't have negative intensities. All right. So I equals 2 is our critical point. Let's just verify that that in fact will give us a maximum. Okay, so we're going to look at dp di. So we can't go down to I equals 0. So let's try an easy point like 1 over here, and let's try an easy point like 3 on the other side. Okay, so if we look at the numerator of dp di right up here, when you put in 1, okay, you'll have negative 100 plus 400, so that is positive, right? When you put in a number like 3, for I, you get I squared will be 9, so you get negative 900 plus 400, so it will become negative. So this verifies that I equals 2 is a maximum, okay? Because the function, since the derivative goes from positive to negative, the function must have switched from increasing to decreasing. Therefore, we did have a maximum. Okay, so I equals 2 is the answer. There's nothing else to find here. So we can just box in that when I equals 2, we will get the most photosynthesis possible. Okay, so after watching this, you should be able to do the first couple homework problems.